the theorem. If we take two injective function and suppose the composition defined, then does the composition will be injective? Did you understand the question?
Yeah.
Yeah. So if G are injective, then G composition F is also injective. Okay.
Okay.
So how we do this? The solution, if they ask this question. So FG are injective function that is given, right?
Huh.
So we prove the composition function is injective. So the solution, we know how to check. We have to start G composition F apply to x1 equal to G composition F applied to x2, right?
Huh.
So what should we get? We get G of fx f of x1 equal to G of f of x2, right?
Huh.
Okay. So what we get now here? Okay. One second.
Okay.
Okay. So now G is injective mean what we get? We get f of x1 equal to f of x2, right?
Yeah.
Since G is injective. Now again we will apply f injective, right?
Yeah.
So what should we get? We get x1 equal to x2. Why? Because
Yeah.
yes, f is injective. So composition of two injective function is injective, right?
Yeah.
Okay. So okay. Give me a second. I got a actually. Just give me a second. Give me a second.
Okay.
Okay. So if we take two injective function, then the composition is injective. What about the surjectiveness, right?
Huh.
Yeah. FG are surjective, then G composition F is also surjective. So if you take two surjective function, the composition will be surjective, right?
Yeah.
So how you do? So see, you can think you have a function like this, that this is F and then you have G, right?
Hmm.
Something, yes, like that. Okay. So how we start? So let you know G belongs to codomain of G composition F, right?
Okay.
Yeah. So then you know what happened? Then G is in codomain of G, right?
Huh.
Okay. So so there exists U belongs to, so let's say you, not U, let's say Y belongs to domain, because surjective G surjective, right?
Yeah.
Domain of G such that you know okay, so we took here a element G. So what we get? We'll get G of Y will be the element Z. This is okay. So we took here G. then it will have a pre-image under G. So this will map to G. Is it okay?
Yeah, it's okay.
All right. So now, so because of G is surjective, just we doing the backward process. Okay.
Okay.
Right. Now, 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 the Y is in codomain of F. So there exists X inside domain of F such that Fx equals to Y. That we can guaranteedly say, right? So
Yeah.
that, yeah. So this will map to Y. Okay. So basically, then what we get? So we getting G equal to Gy. So this is G of Y is Fx, right?
Yeah.
Okay. So we are getting G composition F of X. So this means G has pre-image X in the domain of G composition of F. So it is surjective. So composition of
Huh.
two surjective, yes, done, right?
Done. Yeah.
So now next is, if you take two bijective map, then the composition will be bijective, right? Because of these two, right?
Huh.
Okay. So here note, so composition of two bijective map is bijective. Okay.
So for these notes, you only have the recording. You don't have like the PDF or like the notes you're taking now. Like you don't have a copy of them.
Uh, for the previous one, I have no, but
Okay.
from now I can take the screenshot or image. I can send you.
Okay. Yeah. Please.
The previous class I recorded. You can see in
Okay.
the, yes, YouTube. Okay.
Okay. Fine.
Right. Okay. So right. So let me go to the next topic is here, equipotent set. Okay.
Hmm.
Yeah. Potent of two sets. So we defined, equipotentness of two sets. So we call A is equipotent with B, another set B, if there exists a bijective map, there exists a bijective map F from A to B. Is it okay?
Huh.
Definition clear?
Yeah. Yeah.
Okay. We write it. We write it. We will write it as A equipotent with B, like that. Okay.
Okay.
Right. So we called two sets are equipotent, or A is equipotent with B if we can find a bijective map from A to B. That we write like this: A equipotent with B.
Okay.
Right. So let me tell you some theorem. Then we give some example. Okay.
Okay.
All right. So whenever you want to prove a set, you know this symbol and another set, so you have to find a bijective map from first set to the second set. Okay.
Okay.
Right. So let me tell you some theorem. So first theorem is this, that any set A equipotent with itself. Fine.
Yeah.
Okay. So what will be the bijective map from A to A? You can define basically a map I called the map f from A to A by f of A equals to A. The identity map, right?
Yeah.
This is a bijective map. I am not going to the details proof. It is very easy to prove, right?
Yeah.
So A goes to A. Okay. Second, if A equipotent with B, then B equipotent with A. Fine?
Fine.
Right. So if your set A is equipotent with B, then B also equipotent with A. So from A to B, you have a bijective map. Using that bijective map, you can construct another bijective map. I mean, a new bijective map from A to B to A. Okay.
Okay.
Okay. So what is the proof? So proof, let me write here. A equipotent with B imply there exists a bijective map F from A to B. So we have a bijective map from A to B, right?
Oh.
Okay. We construct a new map from B to A, which is also bijective, right?
Yeah.
Okay. So let Y belongs to B, right?
Yeah.
Then there exists unique, that I am writing like this. There exists unique X belong to A such that the fx will map, I mean X map to Y. Got it? This is because of F is bijective, right?
Yeah.
Yes. Since bijective, so every element will have pre-image. So what we are
Yeah.
doing? Yes. So we have this kind of situation. A is this set and B is this set. So we have a map from this side to this, A to B. This is F map. Now we want to construct a new map from B to A. So how we do this? We have to take any element B, Y from B. Now we have to assign a unique element inside A, right?
Hmm.
So how we are doing that? The assignment. So basically using F. If we take Y in the set B, so then it will have a pre-image here, right?
Oh.
But the pre-image will be unique because injectiveness, right?
Yes.
So there is a unique, that's why I put here unique X such that X map to Y under F. Got it?
Yeah.
Okay. So define G from B to A by how we defining G of Y equal to X if Fx equal to Y. Got it? Which we will
Yeah.
send, yes, Y to X. How we get X? We there, or we know always having a X such that Fx equal to Y because of F is a injective and surjective map from A to B, right?
Yeah.
Yeah, we will send this. So we can check this map is a bijective map. Okay,
Okay.
right. So how we check? Very fast, let me go. So let we take two element y1. Okay, so first injectivity, right?
Yeah.
Let g of y1 equals to g of y2, where y1 comma y2 from the set B, right?
Yeah.
Okay. So then this imply x1 equal to x2, right?
Yeah.
I mean uh, where, yeah, f of x1 equal to y1, f of x2 equals to y2. Got it?
Oh.
So those, so if we know x1 map to y1, then g of y1 is x1, right?
Yeah.
Okay, so this way. So what should we get here? So now this. So what we want to prove? We want to prove y1 equal to y2, right?
Yes.
Okay, so now if you apply f both sides, so f of x1 equal to f of x2. Now f of x1 is y1, so y1 equal to y2. So injective, right?
Yeah.
Yeah. So injectivity done. So now what we do? We do the surjectiveness, right?
Hmm.
So how we do surjectiveness? So we have to take a point here. Let's say we are taking G, right? So let me do it here. Let G equal to in the set A, right? right?
Yeah.
Then, yeah,
Yeah.
yeah. Then f of g in the set B, right?
Huh.
Okay, let u equal to f of g, right?
Yeah.
We're just considering u. So here you get u and u given by f of g, right?
Yeah.
Okay. Now see what we want. We want that if we apply g of, so look at this. So this we consider here, right? Now we want a element here, in the set B that map to the element G by the new map G, right?
Yeah.
Okay. Now see u equal to f of G. So then what we can say, if u equal to f of G, then we can say that G of you know G equals to u. Can we say that?
Yeah.
Is it okay or not? Fine.
Yeah. It's a,
Are you sure? I think I'm writing little different.
no, you said f of z is equal to f of g, right? I mean
Mm-hmm.
g of z, right?
One second, hold on. It's mixing logic. So let me go to the target. What do you want? We select a element here, G. We want a element here, some element that actually here we need, such that if we apply G on this, U, we get G element, right?
Okay.
Okay, that we want basically. Okay, okay, fine. So, okay, so U is this. Now, what will be GU? Yeah, that's correct. GU equals to G, right? That's correct. That's correct. Got it?
Yeah.
Oh, done. So yeah, that we want actually, right?
Yeah.
See, we took here a element G. See, we have a map from this side to this side that we called small g, right?
Yes.
And it's defined this way basically. Okay. Now we want to check it is onto map. So how you do this? So we took a element in this set, say G. Now, G will map to some element inside B. So let's say it is U, right? By
Hmm.
F. So yeah. So U equal to F of G, right?
Hmm.
Now see how the G function was defined. G from B to A is defined at G of Y will be X if Fx equal to Y, right?
Yes.
So now here what we have? F of G equals to U. So G of U equals to G, right?
Yeah.
That we have written, yes. So,
Yeah.
so yeah, yeah, G is surjective. So the map is bijective. So what we getting? We getting B equipotent with A. So if A equipotent with B, then B equipotent with A, right?
Right.
Okay, so because this is very important statement, we will use many times. Okay, so the next statement, let me tell you. So third statement, if A equipotent with B and B equipotent with C, then A equipotent with C. Got it?
Yeah.
Right. So how we write the solution? So solution, A equipotent with B mean what? Imply there exists a bijective map, right?
Yes.
Yeah. Bijective map F from A to B.
Okay.
Yeah. And let me tell you, yes. B equipotent with C mean what? There exists a bijective map G
Yeah.
from B to C, right?
Oh.
So we have the situation A here, we have the situation B here, we have the here C. So here to here we have F, from B to C we have G. Now what we want? We want a bijective map from A to C. Clearly the composition, right?
Yeah.
G composition F, A to C is a bijective map, right?
Hmm.
Because we know the composition of two injective map is injective. composition of two surjective map is surjective. And also we
Yes,
know,
yes.
yes, so from there, yes. Yeah. So what we getting? We getting A equipotent with C. Fine is clear?
Huh.
Okay. I think this is fine. So let me give you one example here. So that it is very important example. So that 0, 1 equipotent with close interval A comma B. Got it?
Okay.
We'll see. Yeah. We have two set. One set is 0 to 1 and another set is A to B. We prove that these two sets are equipotent. So how we do
Oh,
this? Yes. We have to define a bijective map from this to this, right?
hmm.
So we will find a bijective map, bijective actually function f from 0, 1 to A to B. Fine.
Fine.
Okay. So how we define that bijective function? Any idea? For every element x here, assigned a unique element here fx. Can you tell me the formula for fx?
Um,
Mhm. So let me tell you, see, let me tell you the process, how you do this kind of question, okay?
hmm.
So let x is in the interval 0 to 1, right?
Yeah.
So then this imply what? This implies 0 less equal to x less equal to 1, right?
Yeah.
We want a new number in between A to B. So how we can do this? So see, if you look at this, both side we are multiplying by B minus A, okay? Fine.
I don't understand this point.
Okay. So see, here we have A less than B, right?
Yeah.
For interval, always the left hand side is less than right hand side, right?
Yes.
Okay. You will actually, what is the target? Our target for every x in 0 to 1, we need to define a unique element inside A comma B, right? That is the target, right?
Yes.
Okay. So how we doing? So we took a element x between 0 to 1, right?
Yes.
Okay. So x is in between 0 1. Now both side multiplying by B minus A. Inequality no change because B minus A is a positive quantity. Now you can ask me why multiplying by B minus A. You understand after two step, okay?
Okay.
So if you multiple, then this will be 0 less equal to x into B minus A. And this is less equal to B minus A. Both side you add by A. Okay?
Oh,
Plus A. This is what? B minus A plus A. So what we are getting? We are getting A less equal to A plus x into B minus A less equal to B. Is this okay?
yeah.
Okay. So for every x in between 0 1, we are getting a element inside A to B. That's why we multiple by B minus A. Got it?
Okay.
Yeah. So the f defined f from 0 1 to A comma B by how? By defining fx equal to what? Fx equals to A plus x into B minus A. Right?
E plus, yeah.
Yeah, because here if we start with x in 0 1 and then we getting a element inside A comma B by this formula, right?
Yeah, yeah. Okay.
So we are sending x to this. Now you have to check it is injective, surjective, everything, and it is very easy, trivial part. You can check it, right?
Yeah.
So injectivity, how you check f of x1 equal to f of x2 from there, right? So let me go
Yeah.
very fast here. Yes. So f
Okay.
of x1 equal to f of x2. What it give you? It give you a plus x into b minus a, x1 into b minus a equal to a plus, yes, x2 into b minus a. So
Oh,
a cancel out, right?
oh,
x1 into b minus a equal to x2 into b minus a. So what should we get? X1 equal to x2. So injectiveness done, right?
yeah.
Okay, so surjectivity, how we do surjectivity? So let me do it here. So Surjectiveness here I am doing. So let y belongs to a comma b, right?
Yeah.
And consider fx equal to y. So what should we get? Fx mean a plus x into b minus a equals to y, right?
Huh.
So then this imply what? X into b minus a equal to what? 1 minus y minus a. Yes. So x equal to y minus a divided by b minus a. So this is the pre-image
Yeah.
of this x inside the interval 0 comma 1.
Hmm.
Fine.
Fine.
Right. So we got the idea how to check two sets are equipotent, right? Just we
Huh.
have to define a yes bijective map. Okay.
Okay.
Right. So let me go to the next. The next idea is the the cardinality. Okay.
Okay.
Yeah. So it is nothing but the general version of number of element. Okay.
Okay.
Yeah. Generalization of number of element in a set. Got it?
Got it.
Fine. So let me start with the finite set. So so let so a set is called finite set. Okay. Yeah. A set is called finite set. A set A is called finite set if there exists m belongs to natural number. Okay.
Yeah.
And a bijective map f from capital N suffix m. It is defined by 1, 2, 3 up to m. So this n suffix m mean all the number between 1 and m. Okay.
Huh.
Yeah. So these two the set A. So then we called A set is a finite set. If you can find some m natural number such that then there is a bijective map n suffix m to A. Got it?
Got.
So this means you have some collection of object, let's say here, here, here. Those collection you called finite. If you start counting, your counting process will stop after some time, right?
Yeah.
So this is one like this, 2, 3, 4, 5, 6, 7, 8, 9. Here our m will be 9. Okay,
Hmm. Hmm.
right, fine. So now let me tell you some theorem. I will not prove, but I'm telling you. Okay, this theorem. N suffix m equipotent with n suffix n if and only if n equals to m equals to n. Got it?
Okay.
Yeah. So it is natural claim. So basically 1, 2, 3 dot 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 up to m. This from this set to the set 1, 2, 3 dot 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 n. From 1 to 3 dot dot m to 1 to 3 dot dot n, there is a bijective map if and only if m equal to n. Okay?
Huh.
I'm not proving.
Okay.
Okay. So so if A is a finite set, then M is uniquely determined, right?
Hmm.
So let me write down here theorem. This we can prove. If A is a finite set, then there exists unique M natural number, right?
Hmm.
Such that N suffix M equipotent with the set A. Got it?
Yeah.
So so this unique M we call the number of element of A. So the solution, how you do this? So Look at this. Suppose there exists m1 comma m2 belong to natural number such that n m1 equipotent with a and n m2 equipotent with a. Got it?
Huh.
Okay. Now see n. So now look at this. N m1 equipotent with a and n m2 equipotent with a imply what? N m1 equipotent with a and a equipotent with n m2. Is it okay?
Yes.
Because we can switch with respect to the equipotent because we have
Huh.
seen. Yeah. I'm going to back that page. I think you understood, right?
Yes, yes.
Now by this is by the associative property, right? I mean not
Yeah.
associative, you can say transitive property, okay?
Okay.
So this imply n of m1 equipotent with this equivalent this equivalent this. So n of m2, got it?
Huh.
So then this imply what? M of m1 equals to m2. Is this fine?
Yes.
Okay. So if we take a finite set, then we only have one m such that n suffix m equipotent with a. So that m is denoted by m is called cardinality cardinality of a, and it is denoted by it is nothing but number of element of a. Okay.
Okay.
Yeah. Okay. But for infinite set, we know the number of elements since not finite. So how we define this? That is challenging part right here.
Huh.
Okay. So here let me give some example. Let's say a set has with element 1 2 3, and let's say -1 -6. So what is the cardinality of a? How many elements there are?
5.
5. So the cardinality of a is 5. So now if I give you here, let me give you one more example. A equals to, let's say, 1 2 3 4 5. Basically we are taking set of natural number, right?
Okay.
Yeah. Then what should be the cardinality? Cardinality of n, what should it be? So this means you can write also this way. Is it finite or not finite?
Not finite.
Not finite. This is not finite. So therefore, but although the cardinality infinite, we can compare them. Okay, the which is the which set taking, I mean, more element. Okay,
Hmm.
that we will see. So therefore, we need a definition here. Okay,
Hmm.
so here let me write. So cardinality of A less equal to cardinality of B. Okay,
Huh.
if there exists a injective map from A to B. Got it?
Yeah.
Injective map F from A to B.
Injective or bijective?
No, injective, because it is less equal to.
Oh, okay.
Less equal to, yes. And strict less than mean injective, but the map is not surjective. If there exists a injective but not surjective map. So you have a map which is injective but not surjective. Okay?
Huh.
Map F from A to B. Now we call cardinality of A equals to cardinality of B. Okay? I
Huh.
already told you the definition here. If the cardinality equality mean, I did not write here. Let me check. Oh no. Okay, I have to write down here. So this is the first definition, this is the second definition, this is the third. Kindly say mean if there exists a bijective map, right?
Huh.
Bijection F from A to B. Okay,
Huh.
fine. Any questions so far?
No.
So bijective map we will use basically to check that the cardinality of two elements same. I mean the elements of A has a one-to-one correspondence with the element of B. Okay,
Okay.
like that. Then cardinality is same. Yes, fine. That's the idea that you need to solve the homework. Okay.
Okay.
Okay. Let me tell you the Cartesian product.
Okay.
Yeah. Product of two sets. Let A, B are two given set. Now Cartesian product of AB is denoted by A cross B and given by A cross B equals to A comma B, the order pair such that A from A and B from B. Got it?
Okay.
Okay. Now, when you say two element equal, so equality, equality, how you check A comma B, this order pair will be C comma D, if and only if A equals to C, B equals to D. Got it?
Okay.
Right. Now let me write down here theorem. It is from your homework. If
Okay.
yes, A equipotent with B and C equipotent with D, then so here let me write A equipotent with C and B equipotent with D, then A cross B equipotent with C cross D. Got it?
Huh.
Right. Okay, so how we do this? So I think if it is better if I do in the next page, okay?
Okay.
Right. If A equipotent with C and B equipotent with D, then A cross B equipotent with C cross D. Is this okay?
Huh.
So let me write down here the solution. So we need a bijective map from here to here. So there exists bijective map F from A to C, right?
Huh.
And GS from B to D because they are equipotent. Got it?
Yes.
So you have A to C, you have a bijective map, and B to D, you have a bijective map G, right?
Huh.
Defined another map H from A cross B to C cross D by so age of small a comma b. This is nothing but you know A from A, right?
Yes.
So f of A will be inside C, right? See
F of
what?
A.
Yeah,
Okay. Okay. Yeah.
yeah. And this is let me take G of B. So this is the
Okay.
element of C cross D. Got it?
Okay.
Okay. So we check it is injective, surjective. So then we can decide okay this equipotent with this. Got it?
Hmm.
So let me check here injectiveness. So let age of A1 comma B1 equals to age of A2 comma B2. Fine?
Okay.
Yeah, so this imply f of A1 g of B1 equal to f of A2 g of B2. Fine.
Okay.
Okay, so what should we get? Two order pair are equal mean the every components are equal, right?
Yes.
And G of B1 equal to G of
Two.
B2. Yes.
Yeah.
Now F injective, G injective. So what should we get? We get A1 equals to A2. We get B1 equals to B2, right?
Yeah.
So so this means A1 equal to A2, B1 equal to B2 mean A1,
Center.
yeah, A1 comma A2, sorry, A1 comma B1 equals to A2 comma B2. Is this fine?
Yes.
So we start age of A1 comma B1 equal to age of A2 comma B2. We are getting A1 comma B1 equal to A2 comma B2, right?
Oh,
So this is injective.
yeah.
So surjectiveness, how we prove? We have to take a element from the codomain. Let we take a element from C cross D. U comma V belong to C cross D, right?
Oh,
So U belongs to C and V belongs to D. Now,
okay.
yeah, in reverse way, F is from A to C, G is from B to D, are surjective, right?
Yes.
So what should we get? There exists A inside the set A and B inside the set B, such that F of A equals to C and G of B equals to V, right?
Mm.
Okay. So now what happened if you calculate age of A comma B, right? That is nothing but F of A, G of B. Got it?
Yeah.
What is F of A is E, G of B is V, right?
Yes.
Okay. Is this fine? So this is not E, so this is C. Okay,
Yes. Fine.
fine. So surjectiveness return. So age is bijective. So this implies A cross B equivalent with C cross D. Did you understand?
Yes.
Okay. I think we will stop here. We will meet again at night. Then we start homework. Okay.
Okay.
Fine. So take the screenshot. Can you take the screenshot?
Yeah, I was doing now.
1 second. I also taking image. Actually, I can take more class now, but I'm very much tired.
It's okay. It's okay. We can do at night. I
I
just
took
wanted to put
in
the
middle
link on.
actually I feel sleepy, so I don't know.
It's it's okay.
So yes, I took class actually whole day. At night I finish all homework.
Okay. No problem.
We'll go through it. Okay then. I think all concept I finished. One thing I forget to tell you. The
Huh.
countable set, uncountable set. Let me finish that.
Okay.
Yeah. Yeah, here it is. Countable set and uncountable set. So set actually we defined into two parts. Finite set. So if it contains finite number of element, right?
Huh.
Yeah, maybe 10 element, 100 element like this. And infinite set. These two. Now this infinite set we divide into two parts, countable set and uncountable set. Okay?
Okay.
Right. Finite set mean what? you have a set A you called finite if A equipotent with some n suffix m. So 1, 2, 3 dot 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 m. So this means a set is finite if it is equipotent with the partition 1, 2 dot dot m, right?
Yes.
That m is the number of elements. So basically we are counting the elements. I mean the elements of the set A. 1, 2, 3, 4, and it stop at m place, right?
Huh.
Okay, if it never stop, then you say it is infinite set. That we divide into two parts, countable and uncountable. Okay.
Okay.
I don't know how your teacher or your book actually use here. This is little bit confusing part. Different books do different way. Okay.
Okay.
So let me check the countable part they add. Let's check. Okay. A set is said to be countable. Okay, it is countably infinite. Okay.
Okay.
Yeah. Yeah. So that is countably infinite. If by the map, a set is said to be countable or a set is said to be countable or denominable if it is finite. Okay. So this is called countably infinite. So countably, this is called countable infinite set. Okay. Countably, let me write. Countably infinite set mean A equipotent with set of natural number. Got it?
Yeah.
Okay. If we can give a bijective map from set of natural number to the set A, then we called A set is countably infinite set. Okay.
Okay.
Yeah. Now, yeah. Here the book also use this. If you go to the page 165, you can see the terminology varies slightly from book to book. Some other book use countable, denumerable like that. Okay.
Okay.
In this situation. So countably infinite mean the set A equipotent with set of natural number. Okay.
Okay.
And yes, uncountable set mean it is not finite, not countably infinite. Okay.
Okay.
Not finite and not not finite, not countably infinite. Yeah, like that. Fine.
Huh.
Right. And here they use the term countable set or denumerable set. Okay.
Okay.
A is countable or denumerable. Okay.
Okay.
Yeah. If either A is finite or either finite or A is countably infinite. Got it? So
Okay.
anyone. So this means either A equipotent with n suffix m or A equipotent with the set n. Got it?
Yeah.
That's all. So we called a set finite if it is contain finite number of elements, infinite if it is not contain finite number of elements. Countably infinite means the set A is equipotent with set of natural number, and if it is not finite, not countably infinite, we called uncountable. Okay.
Huh.
And countable set mean what? Or denumerable set, either it is finite or it is countably infinite. Got it?
Huh.
Here one example. So that set of all even integer is countably infinite. Okay.
Okay.
Yeah. So that set of all even natural number are, so let me not giving even, let all natural number, set of all natural numbers, odd natural numbers is a countable set, countably infinite set. Okay,
Okay.
right. So first we have to write down the collection of all odd natural number, right?
Yeah.
So let first you write down set theoretically. Okay. So let A is set of all odd natural number.
Okay.
Yeah. So then you can guess the elements of A, how, what are the form of the elements of A, right? Then A contain 1, 3, 5, 7, 9, dot, dot, dot. Is it okay?
Huh.
Right.
Yeah.
So, yeah, this. Fine. So, what do you want? We want to check it is equipotent with the set of natural number. So, we have to give a bijective map from set of natural number onto this, right?
Yeah.
See, we have set of natural number here. Let me write 1, 2, 3, 4, 5, dot, dot, dot. And A set members, let me write 1, 3, 5, 7, 9, like this. Okay. So
Yeah.
let me define a map F from N to A. So let me, can I write here, this place?
Okay. Yeah.
Yeah. Can you tell me a map from this set of natural number to the set of all odd natural number? A map from set of natural number to the set A. So let me make a table. So 1 goes to, let's say 1. Okay.
Okay.
So let me put 1 goes to 1, 2 goes to 3, right?
Yeah.
And 3 goes to 5, right?
Yeah.
And 4 goes to 7. So are you getting
Okay.
any formula? So in
Yes.
general, if you put here x, then where we send it?
It's not 2n plus 1 for just the odd
Plus 1
number.
or minus 1? Because if you take plus 1, then 1 goes to 3, right?
One. Oh, okay. Okay. Yeah. Minus.
Yeah. So you have to take x goes to 2x minus 1, right?
Yeah.
So if you consider this map, fx equal to 2x minus 1, this is a bijective map, right?
Yeah.
You can check. Is it fine?
Yeah.
Why it is bijective? Because you are taking all odd number. Got it?
Yes.
So this is a bijective map. So n is equipotent with set of all odd natural number. Similarly, all so therefore the collection of all odd natural number countably infinite, right? Similarly,
Oh.
all even natural number is countably infinite. Got it?
Yeah.
Now one more question. Let me tell you: the set of all integer is countably infinite. Fine.
Okay.
So that we do. So how we do this? So we have the set 1, 2, 3, 4, 5, 6, 7, 8, dot, dot, dot. Here I am taking, so I am taking here, let's say, first I am taking 0, 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4. Got it?
Huh.
So let's say here 9, 10, 11, 12, 13, minus 4, then 5, minus 5, 6, minus 6. It keep going on that way, right?
Yeah.
So if you try to write this as a map, so this is the set of all natural number and this is the set of all integer. So if we want to write the formula, so can you guess what will be the formula? That will have two branch, right?
Yeah.
So f, see one thing observe that, when you are taking 2, it goes to the half of it. 4 goes to half of it, right?
Huh.
6 goes to 3. all even number goes to its half. Got it?
Huh.
Yeah. So I mean all even number we have to send to the half of it, right?
Huh.
So yeah. So f of x equal to what? We have to
X over.
make, yeah, x by 2 if x is even, right?
Huh.
Okay. Now what happened with the odd? 1 goes to 0, 3 goes to -1, 5 goes to -2, 7 goes to -3, 9 goes to -4, 11 goes to -5, like this, right?
Huh.
So this means the formula if you take, so you just see 3 goes to -1. So we have to make a negative sign before this, right?
Huh.
So you can think 3 goes to 1, 5 goes to 2, like this. So how we get that? So 2 minus 1, we can take x minus 1 divided by 2, right? If x is odd. Is it okay?
Huh.
If you put 1, then you get 0. If you put here 3, then you get 3 minus 1. So 2 by 2 mean 1. So -1. If you put
Huh.
5, then you get -2. If you get 7, put here 7, then you get -3, like that. So the green part, so let me put here the green color, this one, because we are using the green. So minus of, you have minus of x minus 1 divided by x if x is odd. Fine?
Fine.
Right. So that is the idea. So, this is, this map is a bijective map from set of all natural number to set of all integer. So this imply n equipotent with set of all integer. Got it?
Huh.
So Z is countably infinite. So the countably infinite part is done. Okay,
Okay.
right. So there is one more set. So we prove that. So I'll tell you a logic what we are doing basically here. Now next set is, see, we can take a set having one element. We can take the set having no element, right? We
Yeah.
can take the set having two element. We can take the set having three element. Got it?
Yeah.
Like that we can make a chain. So it has no element. So this has cardinality. So this is your A set here. What is the cardinality of A? This is 0, this is 1, this is 2, number of element, right?
Yes.
In general here we can take 1, 2, dot, 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 up to m. So this has cardinality m, right? So it
Huh.
keep going on. Yes. So then first infinite set will be the set of natural number. Okay.
Yeah.
This. So this is sometime denoted by aleph not. Okay, like that. The
O-
cardinality. Yes. Sometime I don't know. I forget to put the notation like that. Aleph not. Okay.
Okay.
The next cardinality that you have now, in between empty set and natural number, there are all finite set. Okay.
Oh.
Natural number is the first infinite set. Fine.
Okay.
Right. Now after natural number, the next infinite set is the set of all real number. Okay.
Okay.
But you can tell me that, okay, what happened with Z? What happened with Q, right?
So.
All, see, since, okay, okay, one thing let me write down here.
Okay.
I think I have written here. Same cardinality. Did I told you? Yes. Here. Two set will have the same cardinality. We write same cardinality if there is a bijective map from A to B, right?
Yes.
Right. So look at this. We know here we have bijective map from N to G. So this set will have same cardinality, that is aleph not, right? Is
Yeah.
it okay? Now what happened with the rational number? Is rational number countable? See, it was very much trivial that the set of integer countable, because we can give this type of bijective map, right?
Yes.
What happened with the set of rational number? So set of rational, before go to set of rational number, let me talk about the positive rational number only. Okay,
Okay.
right. So Q plus. So all positive rational number. We want to check this is countable or not. I mean, the cardinality of Q plus and set of natural number same or not, we want to check, right?
Huh.
So let me listed all rational number in a nice way. So first focus on the, the denominator, right?
Yeah.
Okay. Okay. So how we do this? So let me take here the denominator 1 over 1, 1 over, uh, 2, 1 over 3, 1 over 4. It going on like this, right?
Yes.
So 2 over 1, 2 over 2, 2 over 3, 2 over 4 this way, right?
Yeah.
3 over 1, 3 over 2, 3 over 3, 3 over 4 this. Fine.
Okay.
Then we can give a map from here to here to here like that. Got it?
Yeah.
This way we can give a bijective map. So this is the actually what I'm trying to say. So first we are taking this, then this, then this, then I mean we getting a diagonal. I put this is not proper way. You getting a diagonal, right? So like this,
Yeah.
like this,
Huh.
like this, then four element like this, right?
Yeah.
We can give also a rearrangement of the set of natural number. So you can find a bijective map from n to q plus. Okay.
Okay.
And also, yeah, we know q plus to q minus, we can give a bijective map. X goes to minus x. So basically, n to q minus, we have a bijective map, right?
Huh.
So q plus countable, q minus countable. Now, if you take q plus union q minus, that also countably infinite. Okay.
Okay.
If you add finite number of element with a countably many, set, countably infinite set, then it will still be a countably infinite. So it is countably infinite. So this is equivalent with n. I'm not going to that detail. Just
Okay.
it's okay.
Okay. No problem.
Right. So how many pages I sent to you? This was the last thing. Okay. I sent to you up to this. A cross B. This is the page. Yeah, like that. I'm sending you the image. Also, you can see in the YouTube channel. If, whenever you get time, you can go through. Okay.
Okay.
Yeah. That. So the last part, countable and uncountable. Lots of theorem there are. So maybe when I will solve the question, I'll tell you few more. Okay.
Okay.
So did you understand this symbol A equipotent with B? So this
Yes.
is
Yes.
yes. Okay, that is important. From A to B, you have to define a bijective map. That is the idea. Okay.
Okay.
Okay. So one last question, then we stop.
Okay.
Yeah. So so that so that 2, 3 equipotent with 7, 10. Okay.
Okay.
Yeah. So from 2, 3 to 7, 10, we have to give a bijective map, right?
Huh.
Okay. How we do this? See, we already know from 0, 1 to A, B, we can give a bijective map. That we have an idea, right?
Yes.
X goes to what was the bijective map? That was A plus X into B minus A, right?
Yes.
This is the bijective map. So here what we get, F we can define 2, 3. I mean sorry 0, 1 to 2, 3 by how? Fx equal to what? a plus, so 2 plus x into 3 minus 2. So this is nothing but 2 plus x. Got it?
Huh.
So 0, comma 1 to 2, comma 3, the bijective map is fx goes to, fx equal to 2 plus x. Right?
Huh.
Now, similar, so you can define a map G from 7, comma 10, sorry, again from 0, comma 1, 0, comma, all the map, both map FG are bijective, right?
Huh.
So how you can define fx equal to, you can take 7 plus x into 10 minus 7. So this is nothing but 7 plus 3x, right?
Huh.
Okay. So we have a bijective map from 0, 1 to where? 0, 1 to 2, comma 3, right?
It's f of x or g of x?
Sorry. This is g of x.
Okay.
Yeah. Okay. We have the bijective map f, right?
Yeah.
Now from here to here, 0, comma 1 to 7, comma 10, we have a bijective map, right? G. Got it?
Huh.
Yeah.
Huh.
What do you want? We want 2, comma 3 to 7, comma 10. So if we get the reverse map from here to here, first we apply reverse map, then we
Mm.
go through this. Then we get a map from here to here. Got it?
Huh.
So we need to calculate F inverse, the inverse of F map, right?
Yeah.
So how you calculate? So let me tell you how to find inverse of a map. So fx equal to, how it is defined? 2 plus x, right?
Yes.
So y equal to. So y equal to, you have 2 plus x. So now calculate for x. X equal to what? Y minus 2, right?
Yes.
So what we get? Yes. F inverse of y will be basically y minus 2. Got it?
Okay.
So for convenience, you can write, instead of writing y, you can write F inverse x equal to x minus 2. Is this fine?
Okay.
Right. So from here to here, you have the inverse map, F inverse. Now here you have G map. So F inverse will be followed by G map. Okay.
Okay.
So G composition F inverse. This is a map from 2, comma 3 to 7, comma 10. I forget to tell you, if some function will have inverse, I mean, I think I did with you here. Which example I did? I think, yeah, this situation. I did it. A to B, we have a bijective map. We construct a new bijective map G. That G is nothing but the inverse map. Okay.
Yeah.
That we also prove is a bijective map. So if you have a bijective map, the inverse of bijective map is also a bijective map. Okay.
Okay.
Right. So this is, without doubt, we can believe that this F inverse is a bijective map. So this is a bijective map, right?
Oh.
Why? Because F inverse and G are both bijective. Is this fine?
Yes.
Yeah. Okay. Now let me write down the formula. Okay.
Okay.
So G composition F inverse applied to X. What is this? This is G of F inverse X. Now G of F inverse X is what? I told you X minus 2, right?
Yeah.
Yes. What is Gx? 7 into 3x. So 7 plus 3 into x minus 2. So what should we get? 7 plus 3x minus 6. So we're getting 3x plus 1. Is it equal?
Yes.
So the bijective map, how defined? 2, comma 3 to 7, comma 10. X goes to 3x plus 1. And how did we get it? Using this fundamental concept. Okay.
Okay.
See, if you check, you can see that 2 goes to 7, 3 goes to 10, right? By this map. Fine.
Fine.
Okay. Okay. So did you get the idea?
Yeah.
Okay. So this also I have to send to you. I think how much I send. So this chain is important. Chain is important because we need to do it. So So let me tell you little bit last example how to find inverse of a bijective function. Okay.
Okay.
Yeah, inverse of a bijective function. So all only bijective function will have inverse. Okay.
Okay.
So let me write here a function f from, let's say let's say r minus 1 to, let's say I don't know where will landing. I will tell you. Defined by fx equal to the formula y equal to fx given by the formula x plus 3 divided by x minus 1. Okay, fine.
Okay.
Right.
Fine.
Okay. So check f is a bijective map and find it inverse. Okay. So f inverse x we calculate also. So give me a second. Let me write down the codomain. Y equal to x minus 1, y x minus y equal to x plus 3. So x minus x equal to 3 plus y. So, equal to 1. Yeah, got it. Okay, fine. So r, so let me put here this r minus 1. Okay,
Okay.
fine. So yeah, so okay. So we have a function r minus 1 to r minus 1 defined by this. Okay,
Okay.
yeah, we check it is bijective and we calculate inverse of it. Okay, the solution here. So first check injectiveness. Do I check or you understood injectiveness?
Yeah, I understood.
Okay, surjectivity.
Maybe you do the subjectivity.
Okay, injectivity is clear. F of x1 equal to f of x2 you consider, then imply x1 equal to x2. This
Huh.
part you try. Okay,
Huh.
it is easy. Just simplify, you get it. You did this kind of question, right?
Huh.
Surjective, the surjectiveness if we try, we take a element in the codomain, right? So let
Yeah.
y belongs to yes, r minus 1. So then this imply y not equal to 1, right?
Huh.
This is the codomain. From
Huh.
codomain we are taking. Yeah, from the last, I mean, you can say the second set. Yeah. So now we will find x such that fx equal to y. We start with the equation fx equal to y and we try to find out x. Okay.
Okay.
So x plus 3 divided by x minus y equal to y. So what should we get? X plus 3 equals to y into x minus 1. So what should we get? X plus 3 equal to yx minus y. So we'll get here basically. So x if you factor out then you get y minus 1 equal to minus y minus 3. So what should we get? X equal to minus y minus 3 divided by 1 minus y. So y plus 3 divided by y minus 1. Is it okay?
Yeah.
Now check, is x real number? I mean, is this x is a real number? I mean, in this set? Yes, right?
Yes.
So this is here in r minus 1. So how you check this is in r minus 1? First check it is a real number. Why it is real number? Because y is not equal to 1. So
Uh-huh.
therefore, it is real number, right?
Yes.
And why it is not 1 the expression? So what happened if you take, here let me, y plus 3 by y minus 1 equal to 1. Then what we get? Y plus 3 will get y minus 1. These two cancel out. What should we get? 3 equal to negative 1. Is it possible?
No.
No. So this is the contradiction. In the logical sense, it is called contradiction. So since we getting contradiction, so this is one not possible. So the whole expression is in r minus 1. So we happy. We getting a x, at least y plus 3 by y minus 1. This is the pre-image for y, right?
Oh,
So it is bijective map. So the conclusion is, so F is bijective map. Now, if it is bijective, we can calculate its inverse, right?
oh,
So how we calculate inverse? So let me write down here. We will start with y equal to fx. So then what we get? Y equal to x plus 3 divided by x minus 1. And solve for x. Okay.
okay,
So y minus 1. And people, what people do, they interchange x and y first. That is cleverly idea. Okay.
okay,
First you interchange yes, x and y. So in the place y put x, and in the place x you put y. Then
okay,
solve for y. Yes. So interchanging x and y. Okay.
okay,
All right. So what should we get if we solve for y? X into y minus 3 equal to y plus 3. So xy minus 3x equal to y plus 3. So xy minus y equal to 3 plus 3x. Y factor out x minus 1 equal to 3 plus 3x. Right?
yeah,
So what should we get? Y equal to 3 plus 3x divided by x minus 1. Okay.
so-
So we getting f inverse of x equal to what? This formula. Okay.
oh,
Yeah. Any question?
no,
Okay. The new thing that I used here, in first I interchange x and y, then we calculate, we solve for y, right?
oh,
I here calculate inverse in this place, but in this place I did not interchange. I directly calculate x, and I write f inverse y equal to y minus 2. Then I have to in the place y I have to put x. But if
yeah,
you previously interchange, then you do not need to do that. Okay.
okay,
Right. I think all
oh,
concept we finish. Yes.
yeah, okay, maybe we can stop now.
Yeah. I sent through the. You can see it here in the here. I will send
Okay,
you the also link. Yeah. Tell me.
yeah, that's okay.
All right. All right. Okay. Okay. Fine. So let me go through very fast what we have done here. So we have seen the property of composition of map, right?
Oh,
In the next page, what we have seen, the equipotent of two set. If from A to B you can give a bijective map. And the
oh,
third slide we have seen this, the all property of equipotentness, right? Reflexive,
oh,
symmetric, and transitive. And then this way, the cardinality, all this concept. Okay,
hmm,
fine. Any question?
no,
Okay, fine. All right. So I think we stop here. Okay.
okay, yeah,
Okay. So see you then. 8.
okay, thank you so much.
Thank you. Bye.